Well, thanks for coming back from lunch, and thanks for bearing with me through my technical difficulties. My name is Alan Ott, and today I'll be talking to you about virtual memory and Linux, which is actually a little bit different title than was on the thing, which I think was Introduction to Virtual Memory and Linux, but I am covering that material. So a little bit about me. I'm currently the Linux architect at SoftIron. SoftIron is a startup creating 64-bit ARM servers and data center appliances. We're a hardware company. We're selling hardware, but we're also very strong on software. Many of the people in the company, all the way up to senior management, have spent a lot of time writing software. So we definitely do both, hardware and software. We have one product in the market right now. It's the Overdrive 3000. It's a development server for 64-bit ARM. So it's a 64-bit ARM development server. And we have more products that will be released in the coming weeks. I've done work on the Linux kernel. I've done work in firmware, probably even more work in firmware. I give training, and I've done a lot of work with USB as well. I'm the creator and maintainer of IMStack, which is a USB device stack for PIC microcontrollers that's open source. And I've also done work with 802.15.4 wireless. So we're going to talk about virtual memory for the most part, but first let's begin by talking about physical memory. So some simple systems only have a single address space. So in this simple address space, this single address space, memory and peripherals share it. So you'll have memory mapped to one part of the address space, and you'll have peripherals mapped to another. Many older systems are like this, and then many modern but small systems like microcontrollers are built this way. Well, in a process or in a system like this where you have only a single address space, you don't have any memory protection, right? So processes can stomp on one another, and user space can even stomp on kernel memory. A lot of times that's okay with these kind of systems because if it's a small enough processor, maybe you've only got one process running anyway, or maybe you have a real-time operating system and you're managing a couple of threads, but having one global memory space might not be so much of a limitation on that kind of a small system. So there are many systems with this type of arrangement. So early x86 CPUs, anything ARM Cortex-M, 8 and 16-bit PICs, AVRs, SH1 and 2, and really most all 8 and 16-bit systems. So here's an example of a physical memory map. This is the memory map from x86. It's fairly simplified. Many of you are probably familiar with this, but one of the things you might notice is that you have RAM in two different areas. You have the DOS area down on the bottom, you have the extended memory, and then you also have the high memory. And so there's a lot of legacy that's wrapped up in this kind of memory map. Certainly on x86, and in the old days there were different ways to access different kinds of memory, and a lot of burden placed on software developers. Another thing to notice is that the actual RAM is split by VGA memory and various BIOS memory and registers. So you have to know quite a bit about how the hardware is laid out if you're going to develop directly for a physical memory system like this. And so those are some of the limitations. You know, multiple memory access methods are going to limit portability for your code. Management of all of it is tricky. You need to either know ahead of time or be able to detect the total amount of RAM on the system to be able to use it all effectively. And then you need to be able to keep processes separated too. So if you did development in DOS, you know, there were tricks in order to keep certain things separate from other parts. And of course, you have no protection. So rogue programs can corrupt the entire system. So that's a physical memory or flat memory or single address space. And let's talk now about virtual memory. So what is virtual memory? Virtual memory is a system that uses an address mapping. And this mapping maps virtual address space to physical address space. So we have two different address spaces, virtual and physical. And in a virtual memory system, there's a mapping between virtual addresses to both physical RAM and then also to hardware devices, depending on the architecture. So you have virtual addresses, and some of those virtual addresses address RAM, and others address actual hardware devices and registers in those hardware devices. So an example of some of that stuff is like PCI. You can map PCI memory directly into your memory space. GPU RAM, or any kind of on SoC IP block-based peripheral, so like on an ARM SoC, for example. So there are many advantages for using a virtual memory system. The first is that each process can have a different memory mapping. So that means that one process's RAM is completely inaccessible and invisible to other processes. So this kind of gives you some built-in memory protection. If you can't even see the memory from another process, there's no way that you can stomp on it. Kernel RAM is able to be kept invisible to user space processes as well. So the kernel is protected from rogue user space programs. Memory can be moved, as we'll see later, and memory can be swapped out to disk. And all of this can be done behind the scenes by the kernel, and the user space programs might not even know about it at all, and really shouldn't know about it at all. Another advantage is that hardware device memory can be mapped directly into a process's address space as well. Now, of course, this is going to require the kernel to perform the mapping, but even from user space, you can map hardware directly into your virtual address space and manipulate the hardware directly. Another advantage is that physical RAM can be mapped into multiple processes at one time. So this gives us shared memory. If we take the same physical page frame, map it into multiple different processes' address spaces, they can both manipulate this same memory. Another advantage is that memory regions can have access permissions, so with read, write, and execute. So you can use this to protect the text or code of shared libraries. So you can have shared libraries loaded in a shared memory type way that are protected. You can also protect your program's executable code from overwrite. So like we've talked about, in a virtual memory system, we have two address spaces. There's physical addresses, and physical addresses are the addresses that are used by the hardware. So these are the addresses that are used by DMA and peripherals to talk to one another, for example. Then there's also virtual addresses. Virtual addresses are the addresses used by the software. So in this case, we're talking about load store instructions. Now, I've seen hardware documentation before that said that everything on the system uses physical addresses except for load store instructions. And while that may technically be true, as software developers, load store instructions is kind of where we spend most of our time rather than configuring hardware. So for any process running in user space, almost everything running in kernel space, we're using virtual addresses almost all of the time. So this mapping is performed in hardware, and because it's performed in hardware, there's no performance penalty for accessing already mapped regions. So this means you access a memory address, it's handled completely in the hardware, and there's not any penalty for doing the lookup if the region is already mapped. In the same way, permissions are handled without penalty, and another advantage is that the same CPU instructions are used for accessing RAM and accessing mapped hardware. So any kind of pointers or whatever in C is all going to work the same way. And of course, software during its normal operation will only use virtual addresses. And in Linux, this includes kernel and user space. So this is all implemented by the memory management unit. The memory management unit is the hardware that's responsible for implementing this whole system. It sits between the CPU core and the memory, and most often it's part of the physical CPU itself. On ARM, further, it's part of the licensed core. But different systems and different architectures, it may be a little bit different. On some older systems, there's actually a separate chip. It's important to note that this is something that's separate from the RAM controller. So if you have a DDR controller, that will be a separate IP block on your SoC and not the memory management unit itself. So the MMU transparently handles all of these memory accesses from all of the load store instructions. And it maps virtual memory accesses using virtual memory addresses to either system RAM or to peripheral hardware. It also handles the permissions, and the MMU is what's responsible for generating a page fault on an invalid access. And we'll be talking about page faults extensively. There's also the translation look-aside buffer. So the translation look-aside buffer, or TLB, is a list of mappings, essentially just a list of mappings from virtual to physical address space, and this list of mappings is in the hardware. The TLB also holds the permission bits as well. So there are a fixed number of entries in this TLB, and that's going to vary by CPU. Small CPUs have a small number of TLBs. One system that I've looked at has only 20 entries in the TLB. The TLB is part of the MMU system. So here's a simplified diagram of the memory system. And so we can see we have part of the CPU, we've got the ALU, communicates with the MMU. The MMU consults the TLB for the mappings, and the MMU is what communicates with the memory controller. The memory controller, of course, is what communicates with the system RAM. So that's how all of these pieces fit together. So the TLB, like I said, is consulted when the MMU, consulted by the MMU when the CPU accesses a virtual address. If the virtual address is in the TLB, then the MMU can look up the physical resource, whether it's RAM, a physical RAM address, or if a physical hardware address. It can just perform this lookup, and it can return or store the appropriate data. But if the virtual address is not in the TLB, then the MMU will generate what's called a page fault exception, and it'll interrupt the CPU. So then the page fault exception is going to be handled by the kernel, and there are a lot of different things that the kernel could do with this page fault exception that we'll be talking about. It'll also generate a page fault exception if the permissions aren't correct, and it'll be up to the kernel to handle that as well. So a page fault, as we've hinted at, is a CPU exception. It's generated when software attempts to use an invalid virtual address. And there's really three cases where this might happen. The first is if the virtual address is simply not mapped at all into the virtual address space of the process that's requesting it. Another case is if the process has insufficient permissions for this address, so you're trying to write into something that's read-only, for example. And the third is if the virtual address is valid, but it's swapped out. And so it's important to note here that this is really only a software condition. The CPU doesn't know anything about swapping. It doesn't know anything about whether frames are in RAM or whether they're on disk. All it knows about is whether it has mappings in the TLB for the addresses that you're trying to read or write. So the state of the page frame, whether it's swapped in or swapped out, is something that has to be managed and then handled by the kernel. And we'll talk about that coming up too. So let's talk about virtual memory that's in the kernel and the different types of memory that are in the kernel. So in Linux, the kernel uses virtual addresses just the same as user space processes do. It doesn't use physical addresses directly when you're in kernel mode or anything like that. Everything is going through the memory management unit. In Linux, the virtual address space is split. And it's split so that the upper part is being used by the kernel and that the lower part is being used by user space applications. So on 32-bit systems, by default, this split happens at 3 gigabytes. So 3 gigabytes is C in the upper nibble on the address. So here's what this looks like. We have our virtual address space. And so on a 32-bit system, regardless of how much RAM we have, we always have 4 gigabytes of address space in virtual memory, right? Because we have 32 bits, and 32 bits gives us 4 billion bytes. So we can see here that we have config page offset in the middle, and config page offset is the dividing line between kernel memory and user space memory. By default on 32-bit, like I said, this is at 3 gigabytes. And so the kernel uses the top 1 gigabyte of virtual memory space, and user space processes get the bottom 3 gigabytes of virtual memory space. So on 32-bit systems, this limit, this config page offset, is actually configurable at build time. So when you're doing your make menu config, you can search for config VM split 1G and config VM split 2G, et cetera. And you can use this to actually change where that split is. For the rest of this presentation, I'm going to assume the default values. So I'm going to assume 1 gigabyte for kernel and 3 gigabytes for user virtual memory space. On 64-bit, since we have so much address space, the same rule is in effect, where we have kernel memory on the top, user memory on the bottom, but the split is very high, and it varies by architecture. So you can see here the values on ARM64 and on x86-64. They're effectively high enough that we don't have to worry about what they are, because in a 64-bit system, we have far more address space than we could possibly have conceivable memory. So there are 3 types of virtual addresses in Linux. Now, the terminology varies here, even in the kernel source code. But the terminology I'm going to use comes from the Linux Device Drivers 3rd edition book, chapter 15. And these definitions are somewhat standard. But like I said, you might find different references to these concepts in the kernel. So if you haven't read Linux Device Drivers 3, you can download it for free from lwn.net. There's actually a 4th edition that's in the works, but I can't tell you what the release date on that is going to be. So we have three types of virtual addresses in a Linux system. We have two that are used by the kernel and one that's used by user space. So in the kernel, we have kernel logical addresses, and we have kernel virtual addresses. And then in user space, we have user virtual addresses. LDD3 also talks about bus addresses, which are architecture specific, but we're not going to talk about them here. So let's talk first about kernel logical addresses. Kernel logical addresses, these represent the normal address space of the kernel. So when you allocate any memory from running inside the kernel, inside a driver or otherwise using kmalloc, this will give you a kernel logical address. With kernel logical addresses, the virtual address is at a fixed offset from the physical address. And they're shifted by exactly the page offset. So if your page offset is 3 gigabytes, that means that the byte at 3 gigabytes in virtual memory corresponds to 0 in physical memory. So this makes converting between physical and virtual addresses easy. So this is how it looks pictorially. So we have virtual address space on the left, we have physical address space on the right, and we can see that if we have some amount of physical RAM, this physical RAM is mapped directly into the virtual address space of the kernel starting at page offset. So it's very easy to convert virtual addresses to physical addresses and vice versa. And we can do that in kernel code using these macros. So these macros are PA and VA, and essentially all they do is shift the address up or down. PA, of course, physical address, VA, virtual address. So for small memory systems, and in this case I'm going to say it's a system below roughly 1 gigabyte of RAM, the kernel logical addresses start at the page offset, and they go through the end of physical memory. All right, so if you have 8 megabytes of memory on a small embedded system or something like that, kernel logical addresses will go, in the picture here, from 0 up to 8 megabytes. I'm sorry, from page offset up to 8 megabytes beyond page offset, and they'll correspond to 0 through 8 megabytes in physical RAM. So really, it's a direct one-to-one mapping that's shifted. So kernel logical address space includes not just what's allocated with kmalloc, but what's allocated with most kernel allocation methods. So if you're using caches or slabs or anything like that, we're talking about memory that's going to be in this kernel logical address space. It also includes kernel stacks. So in the kernel, every process has a stack similar to in user space, but the two stacks are separate. The user space stack exists in user memory, and the kernel stack exists in kernel memory. Kernel logical memory can never be swapped out. Okay, and this is an artifact of that basically we're talking about just a fixed mapping between user and virtual. So there's not really any mechanism by which you could swap this memory out. This also means that virtually contiguous regions of memory, so in virtual address space, if they're contiguous, it means they're also contiguous in physical address space. And this is important because things like DMA operations, which operate only on physical memory, need to have contiguous buffers. So kernel logical memory is suitable for DMA transfers. So let's talk about large memory systems. So on a 32-bit large memory system, and in this case we're talking about a system with more than about 1 gigabyte of RAM, not all of the physical RAM can be mapped into the kernel's address space, right? Because if we only have 1 gigabyte of kernel address space, and we have more than 1 gigabyte of RAM, it can't all be mapped, right? We just don't have enough address space for that. Beyond that, 104 megabytes is reserved at the top of the kernel's memory space for non-contiguous allocations. And those allocations are things which use vmalloc, which we'll talk about later, and also when you're mapping hardware devices into kernel memory. So we'll see both of those later. So thus, in a large memory situation, only the bottom part of physical RAM can actually be mapped directly into the kernel's logical address space. Or rather, only the bottom part of physical RAM has a kernel logical address. Now note that on 64-bit systems, this case never happens because we basically have a ton of virtual address space. And there's always enough to accommodate it. So the situation I'm talking about here looks like this. So notice we have a lot more physical RAM now than we did before, but we have the same amount of kernel address space. So that means that the physical RAM is going to be in two parts. The first is RAM with direct mapping into kernel space, and then above that, RAM without a direct mapping into kernel space. So we also call these low memory and high memory. So low memory, of course, physical memory, which has a kernel logical address. When it's used by the kernel, it is physically contiguous. And then high memory is physical memory beyond 896 megabytes. It has no kernel logical address, and it's not physically contiguous when used in the kernel. You can only use this memory through vmalloc. And we only have this condition on 32-bit systems. Because again, on a 64-bit system, we have plenty of virtual memory space. And on a 64-bit system, all memory is low memory. So let's talk now about kernel virtual addresses. We've talked about kernel logical addresses. Now we're going to talk about kernel virtual addresses. Kernel virtual addresses are the addresses in the region above the kernel logical address mapping. So looking back at the picture here, we have kernel logical addresses. This is what's in the area above that. So this is also called in the Linux kernel source code the vmalloc area sometimes. So sometimes you'll see it referred to as the vmalloc area. So kernel virtual addresses are used for two different things. The first is non-contiguous memory mappings. So this is often used for large buffers on small memory systems, which could be too difficult to find contiguous memory for. And so you would allocate these buffers using vmalloc. The other thing they're used for is memory mapped I/O. So this is when you map peripheral devices into the kernel. So if you have a PCI device, for example, and you're going to map that PCI device's memory into your address space, that will use this kernel virtual memory area, or the kernel virtual addresses. So in that case, you use request mem region to map a region of physical memory, or you can use kmap to map pages directly. We'll talk about pages coming up. So let's take a look at the picture here on a small memory system. On a small memory system where we have a small amount of RAM, we can see that we have kernel logical addresses, and then kernel virtual addresses show up above the kernel logical addresses. So the important difference is that the memory in the kernel virtual address area, or the vmalloc area, is non-contiguous physically. So this will sometimes make it easier to allocate. So if you have large buffers, like I said, it'll be easier to find blocks of memory that can be stitched together to create a non-contiguous buffer. But this also makes it unsuitable for DMA. So let's have a look at the large memory case. So on the large memory case, we have low memory and we have high memory, just as we did before. And we also have kernel virtual addresses on the top. But this region is a lot smaller now, right? So in a large memory situation, the kernel virtual address area is smaller because there's more physical memory. And so this is an interesting case where, because we have more memory, there's less space for kernel virtual addresses. And it makes sense because it's a fixed pie, right? We have a fixed amount of address space, and we have more logical memory to use, so we have less virtual memory. Or we have less area for virtual memory kernel virtual addresses in the vmalloc area. And again, on 64-bit, this doesn't happen as the page offset is much, much larger. So we talked about virtual memory as it's used in the kernel. Let's talk about virtual memory as it's used for user space processes. So in user space, we have user virtual addresses. User virtual addresses represent the memory that's used by user space programs. So this is where most of the memory is on most systems, hopefully, right? The kernel exists to serve user space, so hopefully the kernel isn't using most of the memory. So most of our memory is going to be in this user region, and we'll have a user virtual address. And this is also where most of the complication is, because user memory is non-contiguous, it can be swapped out, and it has to be shared between many different user space processes. So user virtual addresses are all addresses below the page offset. And each process has its own virtual memory mapping that's separate from the other processes. Threads, of course, will share a mapping because threads of the same process share all of the same memory, of course, right? In addition, you can create a little more complex behavior with clone as well. So if you've ever used the clone system call, you can set up two different processes, and they can either share or have their own copies of just about every dimension of resource. So unlike kernel logical addresses, which have this fixed mapping like we've talked about, user space processes make full use of the MMU. So that means that only used portions of RAM are actually mapped into virtual memory space. It means that memory is not contiguous, and memory can be swapped out, and memory can also be moved. So again, a lot more complication. Since user virtual addresses are never guaranteed to be swapped in or even guaranteed to be allocated at all, user buffers are not suitable for use by the kernel. So you can't allocate memory in user space and pass it into the kernel to be used as a DMA buffer by default. Each process has its own memory map. So in the kernel source code, if you have a look at the task struct, so the task struct is a structure which represents every process, actually every thread that's running on a Linux system. Task struct has in it some pointers to a struct_mm, and struct_mm is the memory map for that process. At context switch time, the memory map is changed. So this is part of the overhead of a context switch, is that now you're going to use a different memory map. Different mappings will have to be loaded onto the TLB. So going back to the diagram, user virtual addresses, these are in this bottom section below page offset. And remember, each process will have its own mapping for virtual addresses, and the mapping is changed during a context switch. So let's talk about how all of this is actually implemented. So we've talked about the different types of memory, and now we'll talk about the memory management unit, which implements all of this and makes all of this happen. So the memory management unit, as we saw before in the intro, is a hardware component that manages all of these address mappings, maps the virtual addresses to physical addresses. MMUs operate on a basic unit of memory called a page. So the page size varies by architecture, and some architectures even have configurable page sizes. So the most common page size that you'll probably run into is 4K. On ARM, pages are 4K. On x86, pages are 4K. On MIPS, the page size has always been widely configurable. There's a whole bunch of different values you can use for the page size on MIPS. And on ARM64, you can choose between 4K or 64K. So for embedded ARM devices, of course, you can pick whatever you want. On ARM servers, 64K is the standard. So in architectures where the page size is configurable, you have to configure it at kernel build time. So it's something that you would set in the menu config. It's not something that can be changed on the fly. So a little bit of terminology about pages that might trip you up when you're looking in the code is that a page is a unit of memory that's sized and aligned at the page size. Right? So on a 4K page system, a page is a 4K block of memory that's aligned to 4K. A page frame, or sometimes just a frame, refers to a page size and page aligned block of physical memory. So when we talk about frames, we're really talking about physical memory and the slots in the physical memory where pages can go. So in this sense, a page is somewhat abstract, where a frame is more concrete. So a page sometimes will also be used to refer to the data that's in a page. So a page could exist in RAM, or that page could exist on a swap media, for example. In the kernel, you'll also see the abbreviation PFN, which stands for page frame number. And this is often used to refer to physical page frames. So the MMU, like I said, operates on pages. And the MMU maps these physical frames to the virtual addresses. So a memory map for a process will contain many mappings. And a mapping can also cover multiple pages. And the TLB is what holds this in it. And so for each mapping, it will hold the virtual address, the physical address, and the permissions. So going back to our memory system picture here, just as a refresher, we have the ALU, the MMU, and the TLB. So remember, the TLB is what's consulted by the MMU and has all of the mappings between virtual and physical address space. So let's talk about page faults in a little more detail. So when a process accesses a region of memory that's not mapped at all, the MMU will generate a page fault exception. Now, the kernel handles page faults all of the time, and it's a part of the memory management design. So a page fault is not necessarily a bad thing. It's something you want to minimize, but it's basically a fact of life on a multi-process operating system. So things that can generate a page fault, one of them is that the TLB is oftentimes going to be smaller than the total number of maps for a process. And so if all of the maps for a process can't be held in the TLB at one time, that means that some memory accesses are just going to generate a page fault because their map in the TLB is not loaded. And in this case, the kernel will have to fix this up in the TLB, and we'll talk about that coming up. But that's one case where you might have page faults as part of normal operation. Page faults occur at context switch time. So when a context switch occurs, all of the maps for a user space process in the TLB are invalidated, and page faults will happen as memory is accessed. Another use of page faults is lazy allocation, which we'll talk about, where memory isn't actually accessed when you request it. It's only allocated when it's used. So we're going to look at some basic TLB mappings here. We can see on the left we have user virtual address space. On the right we have physical address space. And we have the TLB and the TLB entries, which are gluing all of this together. And we can see we have pages that are mapped on the left. Some of them are a single page. Others are multiple pages. So we can see the area here. We have mapped pages, and then we have unmapped space. So this unmapped space is just virtual memory space that's not usable. On the right here, we have allocated frames. So we can see that these blue frames are allocated. The gray frames are unallocated. We have TLB entries and TLB mappings. Another thing that we can see here is that in user virtual address space, we have virtually contiguous regions that if you follow the lines onto the right, if you follow the mappings, are not physically contiguous. So the MMU can be used in this case to stitch together a whole bunch of different regions of physical memory which are not contiguous and make one area that's contiguous in virtual address space. So again, mappings to virtually contiguous regions do not have to be physically contiguous. So this can sometimes make memory easier to allocate, but there's a trade-off there because it might be easier to put together a non-contiguous buffer, but it's going to use more TLB entries to do so. And of course, if you have more TLB entries, that's going to mean that you're going to have cases where not all of them can be loaded at one time, and you'll have more page faults. So it's a trade-off where it might be easier to allocate the memory, but your application might run a little bit slower because there's more page faults running. And of course, almost all user space code doesn't need physically contiguous memory. You know, if you're making something like a web server and you have a buffer, and you allocate a buffer, it doesn't really matter where the items in that buffer reside in physical memory as long as they're virtually contiguous. So each process has its own set of mappings, of course, and the same address in two different processes will almost certainly map to different physical addresses. So we can see that here. We have process 1. We have memory mapped on the left side in virtual space. And we have the blue boxes mapped in physical space. Process 2, we can see that we are using the same virtual addresses, and they're mapped to the red boxes. So we're using the same virtual addresses to talk to completely different, or to represent different physical frames of RAM. And this is, of course, very common. So let's talk a little bit about shared memory. So knowing what we know about the MMU and the TLB and how all of this works, shared memory is then very easily implemented with an MMU. All you have to do is, in two different processes, map the same physical frame into the virtual address space of two different processes. And the virtual addresses of these frames don't even have to be the same. So let's have a look here. We can have one physical frame in process 1, and it's mapped to a section in virtual address space. And then in process 2, we have that same shared physical frame, and it's mapped to a completely different address. But the point is that this frame is mapped into both processes. Now, in some cases, it may not matter what the virtual address of this frame is, but in some cases, it might matter what the virtual address of the frame is. So if you have a shared memory region, and then inside that shared memory region, you have structures and you have pointers to those structures, within the shared memory region, so maybe you have a linked list or something like that. those two shared memory areas will need to be mapped at the same virtual address. Otherwise, those pointers don't mean anything, right? So in some cases, you have to map it into the same place. Well, fortunately, the mmap system call allows us to request a specific virtual address to map a region of shared memory. So the kernel will do its best to do this, to comply with your request, but in some cases, it can't comply with your request. And the reason would be because that virtual address is already in use by something else. So if you're going to do this and use shared memory buffers where a specific address is required, typically what you'll want to do is allocate and request those buffers early on in your program execution before your memory map gets cluttered up with other things. So the kernel also uses what we call lazy allocation. So this means that the kernel won't allocate pages that are requested by a process immediately. So when you request a page of memory, the kernel doesn't give you an actual frame of RAM right away. The kernel will wait until those pages are actually used. And so this is a performance optimization because any memory that you allocate that you don't actually use doesn't actually get allocated in physical RAM. So you can imagine a case where you allocate a large buffer because maybe you're expecting some data to come in, or you allocate the worst case. If the worst case never happens, the RAM never gets allocated. So how does this work? When memory is requested by a user space process, the kernel will simply create a record of the request in its own page tables. And then it'll return to the process quickly without updating the TLB in the hardware. Because again, we haven't allocated a physical frame yet. So when that newly allocated memory is touched, then the CPU will generate a page fault because the CPU doesn't know anything about that virtual address. It doesn't know that the Linux operating system is using lazy allocation. It doesn't know anything. All it knows is that you're touching a piece of virtual memory that's not mapped. So it'll generate a page fault, and then in the page fault handler, the kernel will use its page tables to determine that the mapping is valid, at least from the kernel's point of view. And then it'll allocate a physical frame, and it'll update the TLB. It'll create a TLB entry with the new mapping, and then return to the user space program. So all of this happens in the page fault exception handler, and the user space process doesn't know anything about any of this happening. It can't even detect that this happened, short of reading the proc file system or measuring the time that was lost. So for processes that are time sensitive, though, you might want to pre-fault pages. So if you allocate a buffer and you don't want to have to be servicing page faults, so maybe if you have a real-time system and you're worried about the time that you would lose in the future and when you might lose it, you can pre-fault an area that you've allocated. So the way to do that is to allocate your buffer and then basically do something like just memset it to 0. So just make sure that you touch every page. And then that will make sure that the page fault happens and then that the physical frame is actually allocated to your process. Now, if you're going to do that, the other thing you want to do is you want to lock all of those pages in physical RAM and make sure they don't get swapped out. So if you have a look at the mlock and mlock all system calls and look at the man pages for those, it'll show you how to do that. So let's talk about the kernel's page tables. So far, we've talked a lot about the hardware, but we haven't really talked about what happens in the software. So the entries in the TLB, like we've talked about, are a limited resource since they're actually part of hardware. There's a fixed number of TLB entries. And of course, far more mappings can be made than can possibly exist in the TLB at one time. So this is a very common case. But the kernel has to keep track of those mappings all of the time. It has to keep track of all of the memory that's used on the system all of the time, regardless of what's loaded into the TLB on the CPU. So the kernel stores all of this information in what we call the page tables. So if you have a look at struct_mm, struct_mm is the memory map for a process, and it has pointers to this VM area struct. So the VM area struct represents a mapping. So since the TLB, again, holds a limited subset of the total mappings for a process, or can, some valid entries will not have TLB mappings. And so when these addresses are touched, the CPU will generate a page fault because the CPU has no knowledge of the mapping, only the kernel does. And then in the kernel, the page fault handler will find the appropriate mapping for the offending address. It'll select and then remove an existing TLB, and then it'll create a new TLB for the page containing the address. that was accessed. And after that, it'll return to the user space process. So observe the similarities here to lazy allocation handling. And it's very similar, except that instead of allocating a new frame, it's looking up the frame that's already been allocated. So let's talk about swapping to disk. When memory utilization is high, the kernel may swap frames to disk, of course. We've all seen this happen. Having an MMU makes this possible and makes it possible. So the kernel, during a swap operation, will copy a frame to disk and then remove its TLB entry. So then that physical frame can be reused by another process. So then when the frame is needed again, the CPU will generate a page fault, and because that address is not in the TLB, of course, and then at page fault time, the kernel can put the process to sleep, copy the frame from the disk into an unused frame, and then it can fix the page table entry and then wake up the process. So note that when the page is restored to RAM, though, it's not actually restored necessarily to the same physical frame as where it was originally located. But this doesn't matter because we have the MMU, and the MMU will simply just have a mapping from the same correct virtual address into the different or new physical address. And in this case, the user space process won't know the difference at all, which is a good thing. So here's the process for swapping out. The first is that a frame is selected for a swap operation. The frame is copied to the swap media. The TLB entry is removed. And the frame is now free. So the frame is now free. The page is stored on the swap media. And the page is referenced in virtual address space only with no TLB entry. And what I mean by it's referenced is that your user space program might still have pointers to data that's in that area. So what happens when it's time to swap in? Well, at some point, your program will try to access memory that's in that paged out page. And when that happens, the CPU will generate a page fault because it doesn't know anything about that address because it's not mapped in the TLB. And then at page fault time, the kernel will copy the page from the swap media into an available frame. Note that it's being copied into a completely different frame than it was before. It'll create a TLB entry for it, and then it will return to user space. And again, your program has no idea that this even happened, except for the time that was lost to handle the page fault exception. So that's user space memory as it's handled by the kernel. So what about user space memory as it's handled by user space? So there are several ways to allocate memory in user space. And we're going to ignore for a minute the familiar C allocation functions like malloc and calloc, because those sit on top of platform methods. So we're going to talk about mmap and break or sbreak. So with mmap, you can use it to allocate and map pages directly into your user space process. And with break or sbreak, you use these to increase the heap size. So let's talk about mmap. Mmap is a standard way to allocate large amounts of memory from user space. So a lot of times you'll use mmap for files. So if you're going to map a file or the contents of a file into memory space. But mmap can also be used to map, can basically use to just allocate and then map physical memory. So if you pass in the map anonymous flag, this basically just allocates normal memory for your process. You can also pass in the map shared flag, and it'll make your memory region shareable with other processes. So break sets the top of the program break. So if you read the man page for break, it says that it increases the top of the data segment. But if you inspect kernel/sys.c in the kernel source code, you'll find that the program break is actually a separate data segment. So calling break to increase the top of the program break effectively increases the size of the heap. The break is the heap. That is the kernel terminology for it. There's also the sbreak system call, and this just takes a different parameter. This allows you to pass in a number of bytes that you want to increase it by, rather than setting the top of the break directly. So break and sbreak use lazy allocation. So if you have a look at mm/mmap.c, and you look in the function doBreak, this is in the kernel. doBreak is implemented very similar to mmap. So what doBreak will do is it will modify the page tables for the new area, and then it'll simply wait for the page fault. It's using lazy allocation. You're not allocating the frame directly. You're just adding it to the page tables, and you're waiting for the user space process to touch that new memory. And then when the user space process touches that new memory, then that memory will be allocated. So optionally, though, so that's the standard method. Optionally, though, doBreak can pre-fault the new area for you and then allocate it. So if you use the mlock system call, you can control this behavior. So if you have mlock set, it basically makes it so that when you allocate memory, you'll get it right away. Or mlock can be used to control that behavior, I guess is more correct. So what about the high-level implementation? So the familiar C allocators, so malloc and calloc and others, will use break or mmap depending on the requested allocation size. So small allocations use break, and they just increase the size of the heap when it's necessary. So a lot of times you can call malloc and calloc, and if you're allocating small things, they don't have to allocate any new memory from the kernel at all, right? Because remember, the kernel and the MMU operate on pages, and pages are 4K. So if you have a 4K page allocated and you're allocating small buffers of maybe 256 bytes, you can allocate one page, and then further calls to malloc don't have to actually do anything, right? Kernel-wise, they just do the bookkeeping and give you new blocks of 256 bytes, for example. So small allocations will either do that, or they'll use break to increase the heap size when it becomes necessary to increase the heap size. And large allocations, it will use mmap. So you can use the mallopt function. So you can, mallopt is not a system call, it's a libc function. And have a look at the mmap threshold parameter to control this behavior. So it'll control when to use break and when to use mmap. So another user space concept is the stack. So in user space processes, your stack starts out small, and then your stack will grow, right? So in C programs, at some point there is a limit to the total stack space, but most of the time we write C programs as if there will be enough stack space, and that the stack will grow to accommodate our program. So how does this work? If we have a stack that can grow and memory is not allocated for it, what's the mechanism by which this happens? Well, fortunately, the MMU, like with everything else, is used for this. And so if a process accesses memory that's beyond its stack, then the CPU will generate a page fault, right? Of course, because we're accessing memory that's not mapped. Well, the page fault handler will detect this. It will detect that the address that was trying to be accessed is just beyond the end of the stack. It will assume that, oh, okay, we need to just increase the stack now. We need to grow the stack. And it will allocate a new page to extend the stack. Now, when we allocate a new page to extend the stack, this, of course, isn't going to be physically contiguous with the rest of the stack, but the rest of the stack is probably not physically contiguous at all. And of course, if you're using stack for anything that needs contiguous memory, you're doing it wrong anyway. But it's worth pointing out that when you allocate this memory, it will be virtually contiguous and, again, not physically contiguous. So this is all done in doPageFault. doPageFault is a platform-specific function. And for ARM, you can find it in arch arm mm fault.c. And so if you open up that function, you search for stack, you can see that it does exactly what's listed in the slide here. So that's all for today. We've talked about physical memory, virtual memory, kernel addressing, and user space as well, swapping, and user space allocation. Are there any questions? Yeah. Did you say continuous memory allocation? Contiguous memory allocation. The question is, with contiguous memory allocation, is that part of the kernel or? Where in the kernel does that go? What part of kernel memory? When you allocate contiguous memory from user space? CMA is a combine option. There's also a command line. Oh, that I don't know. So the question is about a kernel command line contiguous memory allocation. I don't know about that specifically, but I have to consult the code.
It moves physically allocated pages, so it goes through the physical memory, finds the free block, and tries to move the stuff to make the continuous block larger.
Oh, so it's like memory compaction.
Yeah.
Okay. Yeah. So did you hear the answer? Yeah. Any other questions? Yep.
So is it possible anything to skip the page fault handler and crash
Is it possible to skip the page fault handler?
Something escape, not handled by the page fault handler.
Is it possible to have a page fault that's not handled by the page fault handler? Yeah, so if you have, if you try to access memory that is not been allocated in your address space and the kernel doesn't know anything about it, it's not using lazy allocation or anything like that, like a bad pointer, for example, it'll generate a page fault, and then the kernel will decide that I have no idea what this is. This isn't a stack expansion, this isn't something that's just not allocated yet or anything, can't figure it out, then that's when your program will crash. The kernel will terminate your program.
So that's because you have an uninitialized pointer or something on the pointer. Something in the operation of the kernel itself that your app does not give you. For example, context switching. If you do context switching and your address space is invalid, is that guaranteed to be handled correctly?
So the question is about, so like context switching, during a context switch or after a context switch. Right, so after a context switch, nothing is mapped, and then a page fault is required to start mapping your process's memory back in again. And so the question is, can something happen there that can potentially crash your app? Well, no, I mean, short of a bug, no. So the idea here is that your program is able to run as if there's not anything underneath it that's managing the memory or performing scheduling or anything like that. So you write your C program and all this stuff is handled under the hood. Yeah. Any more questions? Are we? Oh, I'm 5 over. Okay.
So a short question about the stack. When the stack is growing, we are allocating the next page. Are there some situations when the page is free or it's still allocated?
Yeah, are there situations when the stack is freed? So if the stack goes up and grows and comes back down, I can't say for sure. I haven't considered that. So, all right. Hey, thanks for coming out. I've got my contact information here. Thanks.